Hi, this is my Lab 2 presentation. So the experimental section for this lab was the exact same as in Lab 1, so I'm going to go over it pretty quickly. Basically, we give an electric charge to pieces of tape and attempt to make one charged piece of tape float above another charged piece of tape due only to the electric field of the lower tape. We then measure the separation distance between the tapes at which the top tape floats, and use this distance to calculate the charge on the tape. This lab is different from Lab 1 because in the coding section of this lab, we no longer model the tape as a point charge like we did in Lab 1, but rather as a collection of many point charges. Here's a quick picture of the experimental system. The top piece of tape is floating above the other due to the electric field of the tape I'm holding. So the fundamental physical principles involved in this lab are, of course, electric fields, electric force on a point charge due to an electric field, the force due to gravity, the fact that when the upper tape is floating, we know the net force on it is zero, so we know the magnitudes of the electric and gravitational forces acting on it are equal. And finally, what makes this lab different from Lab 1, the idea that you can model an object with uniform charge as a collection of many infinitesimal point charges, each with charge dq, creating an electric field dE, and add all of these fields up to get the total electric field at an observation location. So now we should discuss any assumptions we're making. For the experimental section, we're assuming that a charged piece of tape acts as a point charge. However, we're no longer making this assumption for the computational model. We are still assuming that clear tape is about 1 gram per meter and that each piece of tape used has about the same charge. Now to the experimental results, which are all the same from Lab 1. The length of one piece of tape was about 0.2 meters, the mass was about 2 times 10 to the negative 4th kilograms, the separation distance at which the upper tape began to float was about 0.027 meters, the magnitude of both the gravitational and electric forces on the upper tape was 2 times 10 to the negative 3rd newtons, and the charge I calculated for the tape was about 1.3 times 10 to the negative 8th coulombs. So now for the interesting part of Lab 2, the coding section. First, I defined some constants, including the mass of the tape, the number of point charges to model the tape with, which I chose 10 point charges for, and the charge of the tape, which I got using guess and check until the electric force magnitude was equal to the gravitational force magnitude in the program's output. I also defined a function that calculates the electric field at a location made by a given charged particle. Next, this function is used to create a line of n point charges with the given position, axis, and total charge. We then make two statements that use the function to create the tape objects, which are lines of point charges representing the pieces of tape. This section of code is where the bulk of the calculations happen. Basically, there are two loops with one nested inside the other. The outer loop iterates through each point charge dq in the top tape. Then for each point charge on the top tape, the inner loop iterates through each point charge dq in the bottom tape and calculates the electric field at the location of the top point charge due to the bottom point charge. It adds all of these electric fields together to find the net electric field vector for each top point charge due to the entire bottom piece of tape, and it makes an arrow for each of these. It also adds them all together to keep track of the total electric field for the whole top piece of tape. Finally, the code makes arrows for both the electric force and gravitational force acting on the top piece of tape, and prints the magnitudes of each. Here's the output of the program. The green arrows coming from each of the red point charges represent the electric field at the location of each point charge due to the bottom tape. The white arrow is the electric force on the top tape, and the yellow arrow is the gravitational force on the top tape. Note that they have the same magnitude, which is why the top tape is able to float above the bottom tape. So, what if I had modeled each tape as a single point charge like in Lab 1? Well, the calculated charge would have been equal to the experimental charge, which was calculated with the point charge model, so it would have been 1.3 times 10 to the negative 8th coulombs instead of 3.9 times 10 to the negative 8th coulombs. Why do these estimates differ? Well, it makes sense that the charge calculated with the line charge model is about 3 times larger than the charge calculated with the point charge model, because when we model the tapes as single point charges, they're very centralized and close together, so the charge won't have to be as big to produce the necessary electric force to make the upper tape float. However, when modeled as a collection of point charges, everything is more spread out and farther apart, especially near the tape's edges, so there needs to be a larger charge to produce the same electric force. The line charge model should be closer to the real value for the charge because this model is more realistic than the point charge model. In reality, the tape's charge is spread out across its entire surface, so modeling it as a collection of point charges spread in a line, despite not being a perfect model, is more accurate than modeling it as one single point charge like we did in Lab 1 and in the experimental section. Thanks for watching!